Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
G'day everyone, welcome back to Mathematical Statistics. Thanks for all coming along. And a few housekeeping things. The midterms have been graded, and also there's an official process for viewing those in tutorials that's followed, and you can ask for a remark if there's anything you're worried about in that. And also the assignments have recently been finished grading. You should be able to see them in your tutorial this week, and the first person to ask about that is your tutor if you have any questions, but you're also most welcome to consult me in my office hours on Thursdays at 10 o'clock. Now, the other thing, thanks to your feedback, those who filled that in, I might make some changes depending based on what you've suggested. And we do have a lot of material to get through for the second half of the course, so I'm not going to spend a lot of time talking about more administrative procedures for now, but you do know there's another assignment that hasn't been posted. Obviously you'll get at least 2 weeks to do that, and that'll be due in week 10. Now let's go on with, we were sort of in the middle of chapter 5, which is multivariate distributions. And what we hadn't talked about was the continuous case. It's showing here, but not up there, so let's get that working. Sorry about that. Should start any moment now. And we already talked about the discrete case of multivariate distributions. A discrete multivariate distribution was, well, multivariate means you have multiple variables, simple as that. And typically we talked about the 2 case, but it's actually the same in any number of dimensions. The discrete case was when there was a countable list of possible values. It turned out it was the same to have discrete multivariate random variable is the same as each individual variable x, y, z, and so on, all being discrete, separate. That's the same thing. Now, that's not the case for continuous, so we need to do a little bit more care, and much like the case when we were just talking about one random variable, I want you to be aware that this is not everything that's going to happen. These are just the 2 nicest cases, and there are practical reasons why you might have neither a continuous nor a discrete multivariate distribution. We're not going to talk about it a lot, but so just to remind you, discrete, there is, so multivariate, the general case is of course when you have n variables all placed together, all xi's, if each of them are discrete, that's just the same thing. So countable list of possible values. Continuous, okay, a multivariate distribution is going to be called continuous if there exists a multivariate or joint. Remember, joint is a shorthand we often use to indicate we're talking about the multivariate distribution. Joint probability density function, which, as always, f apostrophe n as function. So as always, we abbreviate that as PDF. So a joint PDF, f, which I'll always use lowercase f, subscript x1, so you do subscript which variables you're talking about. It has to have n inputs as well, 2 in the bivariate case. Now, what can I say about this so far? Much like the one variable case, first of all, it should always be non-negative. And don't get confused about the word continuous. The density function itself does not have to be a continuous function. If the variable itself is continuous, which means there's no chance of landing at a particular point, but the density function doesn't have to be continuous. We saw that with the uniform variable as a non-continuous density function. But, okay, so it doesn't have to be continuous, does have to be greater than or equal to 0, such that the main thing is the analogy to, with one variable, I'm just going to write a whole lot of intervals. Now, you might be sick of me talking about intervals, but it's just a quick way of including all cases. Whether it goes down to minus infinity or not, it's still going to be true. x1 is in interval 1, x2 is in interval 2, all the way up to xn is in interval n. And how are we going to do this? The way you should think about the density function is you should think of it as, I'm going to draw the n equals 2 case. And then you'd have your x1 axis, which we'd often just call x. We'd have our x2 axis, which we'd often just call y. And then the height axis, I'll imagine that to be the z-axis. So z is height here. Just imagine x, y, z, except I'm calling it x1, x2, z. And the height is going to tell me the density function, you're going to plot the function z equals f with appropriate subscripts. Sometimes we omit subscripts of x1. Well, in this case, it's just x1 and x2. Maybe I'll say that here. We're just talking about of x1 and x2. Then this is the bivariate case. And what does a function of two variables look like? It looks like a surface, a height. And that, you'll notice the density doesn't have to be less than or equal to 1, because it's only the total probability less than or equal to 1. The density could be quite high. It just means locally there's a high chance at that point. So I'm going to draw an image of that, and I'll apologize that my surface won't be that great. I'll try to do it in red. And let's talk about this will be a bivariate random variable that's typically around this red point there. And so its highest peak will be sort of above that point. And then I'm just going to draw cross sections of that. Just a little bit lower here, a little bit lower, and then a little bit lower. So that's what it looks like in this direction. And then maybe a little bit lower behind, that. So a bit hard to draw. And now I'm going to draw those would be the cross sections x2 equals constant, or y equals constant. And then I'm going to draw the cross sections x1 equals constant. They're going to look a bit like this. So these are horizontal cross sections. So this look like. If you want to draw more surfaces like this, you can use something like Mathematica or R, but it's not part of the course to draw them in. Right. So since that's a bit hard to see, I'm going to maybe in green. I'm actually trying to draw something that looks like a very specific density here, the joint normal density, because that's the one we care about the most. But in general, the joint normal density. So if I were to draw radii around that point, it would be like that. So this is really looking like quite a high mountain there. So it's sort of like a big mountain range. It's quite low here. Now all of these heights have to be greater than or equal to 0. That was one of the conditions. So in the green you can sort of see a little bit of the bump and the peak above that point. So not all joint densities need to have a single peak or anything like that. That would be called being unimodal. But it's a very classical shape. Now what is the key point? I'm going to do the key point, which I'm filling in the curve here, which in the line here. The key point is how to find the probability of lying under a certain region. And how you find that is you find the X region, so maybe the chance of lying in this rectangle here, it's kind of a cross section looks like that. I could do all the X bits look a bit like that. The smaller you cut your rectangle, the closer it is to straight lines. And then I'm going to project that down. Now I don't actually care about surface area or anything like that. All I care about is the area of the rectangle and the height. So I've got the surface looks like this bent mesh shape thing, and then there's this rectangle underneath, which is simply the projection onto the XY plane of the same thing. Now, it is the volume of that segment that is the exact probability. So you imagine I've got that, maybe I'll just do the volume in sort of shaded in black here. I have to take the volume of that whole segment here. It's a 3D region. It's bounded by the XY plane on the bottom, X1, X2 plane on the bottom, and it has vertical cuts along each of these rectangles. And then the surface is potentially a curved surface, but that's fine. We can still find the area under a curved surface. And as you would know from integrating, you can integrate a function of two variables. First with respect to one of the variables, second with respect to one of the other variables. And I'll just write x1, x2. The subscript I'm omitting just for space, dx1, dx2. So that would be over the x1 here is integrated over the interval I1. x2 is integrated over the interval I2. So in this context, that would be the interval I1 on the x1 axis, and that would be over here, would be the interval I2 on the x2 axis, roughly. I mean, forgiving the inaccuracies in my picture, but effectively that would be the region that it is, and it's much like area under the curve was probability in the one-dimensional case. Volume under the curve is the probability in the bivariate case, and in general, it's hard to, you can't imagine the drawing of it because you need more than 3 dimensions, but in general it would be the hypervolume, or the n+1 dimensional volume would be in general what the probability is. But there's no need to talk about n+1 dimensional volume because I can just write it as an integral, and integrals make sense without any geometric interpretation. So if I had n variables, it's dx1, dx2 up to dxn, and of course I have to make it n integral signs. So integral over I1 first, and then integral over I2, integral over I3, all the way up to In. So very complicated in the n-dimensional case. Just the bivariate case is worth bringing out as a special case because it's so common. The probability, I'll just write it with x and y to make it simpler. Let's even write it this way. X to be from A to B and y to be from C to D, to make it more concrete, is an integral, and you just have to think about each variable dx and dy, density f of x, y. Okay, and then I just have to think about the inner integral as an x integral. X is allowed to go from A to B. As always, it doesn't matter whether you include A or exclude A, it's the same. And y goes from C to D. It doesn't matter whether you include C or exclude C, it doesn't matter. So that bivariate case is probably worth remembering in its own right. It's just a special case. Now, you'll actually notice this wasn't even a theorem. This was a definition for all intervals. So intervals are, as always, our proxy for a region that you want to be in. You could add up lots of intervals. I1 up to I. So that's the definition of a continuous random variable. Now, it is a sad fact that not all multivariate distributions you care about are discrete or continuous. Now, that doesn't mean they're not multivariate distributions. It just means the formulas we're going to go on and do aren't necessarily valid. There's still not all multivariate distributions of interest. Not even the bad ones, but many are discrete or continuous. And this is so easy to fall afoul of that I want to give you another example. There are even some multivariate normals that are called degenerate multivariate normals that are not continuous distributions. And I want to show you
So let's give an example. Let's just say, I won't do the normal case for now, I'll just do U is uniform 0, 1. Okay? Remember, a uniform random variable, equally likely to be every spot, well, within every region along that interval of the same length. And let's call that U1, and then U2, it's easy to do U2 equals U1, which is the diagonal case. Let's do something slightly more interesting. U2 equals 1 minus U1 is also uniform 0, 1. So if they were independent, then the joint distribution would actually be continuous. We'll get to independence later, but independence, just as for the discrete case, you multiply mass functions, you also multiply density functions. So if U1 and U2 were independent, which they're not, you would get the joint density very easily. So here's the key thing. There is no joint density. By the way, they're not discrete, of course, because U1 is not discrete, U2 is not discrete. There's no joint density function for U1, U2. Now, remember that our definition is the word continuous means there is a joint density function. So those are identical. So to say that there is no joint density function, i.e. They are not, and let's put in the adverb jointly, because that's they're not jointly continuous, even though they are separately, and we have a more probabilistic word for separately than separate. Review from last time. When I have a bivariate distribution and I'm saying forget y, just talk about x. Or forget x, just talk about y. There's a word for that. Marginal, yeah. Even though they are marginally. Okay, so marginally is, in this context, means separately or by themselves. Continuous. Okay. And to understand that, I just want you to think about where they lie once again on a kind of a graph. But here we won't be able to draw a density function because this is kind of the U1 axis. This is the U2 axis. This, I guess, Z as before. The U1, U2 axis. Well, what it is, we know that marginally, I'm going to draw marginal distributions in red so that they don't distract overall. Overall, it's marginally uniform U1. So if I had to do just on the U1 Z-axis, it would kind of look like that. Okay? If I just got U1 and I didn't do U2. And then if I just did U2 and didn't do U1, it would look like that. So, because 1 minus a uniform 0, 1 is also uniform 0, 1. So that will look like that. Okay? But jointly, what happens? Well, so far from being independent, if you know the value of U1, you know the value of U2 there. They're perfectly negatively correlated. Rho equals minus 1. We'll talk a bit more about correlation later. But that means that if you had to sketch where they lay on the field, you would try to do some kind of thing looking like this. It would sort of be a vertical wall like that. Does everyone see that? That's U0, U1 equals 1, U1 equals 0, U2 equals 0. The wall, it just always lies on this line connecting U1 equals 1 and U2 equals 1, because it always lies on the line U1 plus U2 equals 1. So that is a lower dimensional subspace, if you like, or a lower dimensional subset. That's a one-dimensional subset. So jointly continuous variables always lie smooshed out in all n dimensions. This one is not smooshed out. It's only stretched out along one dimension rather than two dimensions. So that's sometimes this is called degeneracy. Okay, so that's just a mathematical term that means whenever something doesn't have the full number of degrees of freedom, we tend to call it degenerate. For instance, a degenerate triangle is a triangle where the three vertices are collinear. It's not really a triangle at all, but something. Yeah. So degenerate is whenever you have a fewer dimensions present than would actually be in general position. General position means you have all n dimensions. So this is not general position. It's not allowed to vary in two directions at once, only in one direction. So that, unfortunately, as a pair, is neither jointly continuous nor jointly discrete. It's still a perfectly valid pair of random variables. I'm just saying that as a cautionary tale to say that not everything that is multivariate will submit to the formulas I'm about to I'm about to give. But luckily, the formulas are very, very concrete in the case that we're going to do. So before I do that, let me just, it's always nice having examples. Uniforms. Let's, I could do uniform in a rectangle, but that would be kind of easy because the x would just be uniform in that rectangle and y would be uniform in that rectangle and they'd be independent. You sort of multiply the constants, you get a constant. What's kind of interesting is you can do a uniform over a region R where, let's just do the bivariate case, is a region in the plane. I'm not going to elaborate exactly on what region means. It's a subset, but maybe a nice subset so that you can find the area of a subset. It's a technicality that not every subset of the plane is suitable for finding the area of that subset. But let's assume that it has an area. If the following is the density. The density of the pair xy at a particular point is going to be, it better be a constant on the region and 0 if the point, remember it's a two-dimensional thing. If xy does not lie in the region, the density will be 0. So there's no chance of lying outside the region. And inside the region, well, it had better integrate to 1. You see, going back to the previous page, it went without saying that the integral of this over the whole real line, if instead of the integrals you have the whole real line, if you put all that together, it has to be 1. And that just went without saying because that's the probability of the point lying anywhere at all, which is the probability of the whole sample space. So while it is an important fact that I'll just say, it doesn't, the definition ends here. I can, I'll just put the fact here because it's quite, regardless of how many, I'll just say, if I integrate with a subscript of RD, I need to actually do d-fold integrals if you need to do that, of f of x. This is a shorthand I'm using. If I do x with a underline or under twiddle, that means a d-dimensional point or a vector dx. So sort of d-dimensional integral equals 1. So that's that fact, is the axioms of probability number 2, that the total probability is 1. So this integral over the whole space or the whole plane in the bivariate case is always 1. So to make that satisfied in this case, I want it to be a certain constant if x, y is in R, but it has to be the case that integral of f x, y, dx, dy. So this is an area integral. Sometimes people call this dA, area, dx, dy. Over the whole real plane, x minus, has to be equal to 1. Just remember that. So that'll tell me what I have to put in here. I want it to be a constant because I want it to be equally likely to be everywhere in that region. Let's have a little cartoon of the region. And I said it's a region that has an area. I want it to be equally likely by area to lie everywhere in that region. You start to appreciate the words by area, by volume, by mass, all those kind of things, because when you do equally likely by volume, it's not the same thing as equally likely by mass. It's like all those medicines you look at, they have to specify whether it's per volume or per mass. So we're talking about equally likely per volume. Every little, or per area I should say. Every little square of area within that region is equally likely to occur. So there's some constant I want to put in here. 1 over the area of R. You see? Because 1 over area of R is the constant such that integrate the constant over the region, integral of 1 over the region is the area. So this is the constant that it has to be. So that's an example of uniform. Now, in the case of a rectangle, it is just an independent uniform in each variable. The interesting thing is that if R is not a rectangle or something that's kind of rectangles put together in a window pane-like pattern, like you could have a window pane, that would be like a rectangle minus some strips. But if it's not a rectangle or a generalized rectangle, then x and y are not actually going to be independent. Because you might think, why are they not independent? Well, if x is along this horizontal line here, sorry, if y is at this point, then there's a whole lot more different values that x could be compared to up here, right? So it's actually going to be the marginal, what that says is the marginal distribution on y will not be uniform. The marginal distribution on x will not be uniform in this example. In fact, we'll be able to calculate this with one of the formulas in a moment. The marginal distribution will reflect the width of the region at that height. So if the width is not constant, then the marginal density is not constant. Okay, so that's our first example. Now let's get on to the concrete things that you actually want to calculate, which are the marginal distributions. These are quite easy, as always, because we do have a precise description of this. From now on, just to save notation, I'm going to do the two-variable case, or y ignoring, that's what's meant by margin. Okay. So I just have to say, to get to the density, I'm first going to write down probabilities, because remember, densities are what you get when you write probabilities as integers. So the probability that x is plus, I'll just say epsilon, because epsilon is often a small amount, and y is, if I'm ignoring y, that's the same thing as saying y can be anywhere from minus infinity to infinity. Okay, maybe not equal to that. That is equal to, if you recall the definition of joint density is just that you can always express the probability as the volume under the surface, or the integral under the surface. So y is going from minus infinity to infinity, x to x plus epsilon. Now, it's a fact about these integrals, so long as you're integrating non-negative values, I'm going to have to use a new letter here. Let me call it u comma y, because x is taken du dy. So that's saying y can be from minus infinity to infinity, u can be from x to x plus epsilon, f x y. So that follows straight from the definition of joint density. But the great thing about integrals, if the limits of integration don't depend on one another, which is pretty much the same as saying it's a rectangular region, then I'm allowed to do it in either order. So I'm also allowed to say this is the integral from x to x plus epsilon. Oh, and the other thing that's very important is that the integrand is greater than or equal to 0, so there's no issues of positive and negative cancellation. So this is a non-negative integrand. I'm allowed to switch the order of integration, and that makes things a bit nicer for me. f x y u y d y du. So I'm just going to, this is an interesting function, and so I could introduce a new name for it, but there's no need to introduce a new name for it, because it's a fact that this is x to x plus epsilon du. So the probability that x lies in a particular interval x to x plus epsilon is equal to x of u. So what I mean to say is that f x of I'm not going to use the dummy variable u anymore. I'm going to use the original variable x is equal to integrate over the whole real line of the y's, fy of joint density x comma y dy. So you integrate out the variable that is of no interest. Now that should look familiar. I'm going to give you a flashback. Now, if you don't understand the reasoning here, maybe you can just remember the formula, but the reasoning is, I've found a function. I've defined fx of u to be that integral, nothing else. Find fx of u to be this integral that I put in dotted lines. And then whatever that function is, it's a function, it exists. You can always integrate a non-negative function. And it's a function such that whenever you put it in for x going from x to x plus epsilon, you get the probability of lying in that interval. So that's uniquely determined. That's the only function with that property is the density function. So the next thing I wanted to say, so that's one formula. So similarly, if you were wanting to do the marginal distribution of y, fy of y is equal to, you integrate all the x variables that occur. So this time fx of joint density fxy of xy dx. So you integrate out the variable that is not of interest. And I'm just going to remind you what happened in the discrete version before the break. We said the similar thing in the context of probability mass functions. You see why I like to distinguish p from f, because this was the mass function. I summed over all possible values of x, whatever they are, countably many, p x y of x y, and then I don't have to do a d anything because I'm just summing rather than integrating. So in the case of discrete, you sum out the irrelevant values. In the case of continuous, you integrate out the irrelevant values to get marginal. Okay. Next thing about marginal densities. Okay, so let's even since I mentioned the example 1, I might as well actually talk about what I said in words. This is x and y, so this will be example 1. Okay. Where it's a region. Now, I didn't actually say what region it is, but I can give a description of what the density is. The marginal density of x that's not even. I'm going to do the one that I drew, which is the horizontal marginal density of y. So ignoring the possible values of x, I have to integrate out over it. So that is integral over minus infinity to infinity of fx y x y dx. And then I have to figure out what that means in the context of this region in the plane. Well, that is equal to the integral over the set of all x values such that x, y is in R. So this is a horizontal slice of the region. And then I have to multiply by the density is 1 over area of R on that slice, and it's 0 elsewhere. dx. Okay? So that equals length of slice at height y divided by area of R. So it's slice of R, of course. You know, R is a region. It has slices at each height. Each of them has a length. Now, there's not two segments. You'd have to add up those two segments. And then, how is this relevant? It kind of manifests in the way that if you integrate out all the lengths of the slices of a region, that gives you the area. We know that you can calculate areas by slicing whether horizontally or vertically. So if you're being technical, it's an application of Fubini's theorem, but it's just kind of common sense. And so that's what it is in that example. Now let me give you another relation, which is that the what we already know that it's true is that integral minus infinity to infinity of, so matching what I said in words of f y of y dy equals 1. That's just every distribution has that property up to and including joint distributions. In this example, integral minus I'll just say minus infinity to infinity. This is okay because length of slice at height y divided by area of r dy equals 1, which is another way of saying that the area of r is equal to the integral of... Now you might say I should integrate only over the heights that are in the region, but of course if I do y below the bottom of the region I'll get length 0, and yeah, so that's length of height y slice at dy. Okay, so that's marginal, and we've done a lot of examples. Possibly more interesting than marginal is conditional. So let's talk about conditional distributions. Now, I want... this is where the complications start to come. And the conditional distributions... Oh, before I say that, I just want to give you... I don't even want to do an example of this, but we arguably already did an example of this. So this is just a reminder, if fxy of xy is equal to constant times g of xy. So you might have unknown constant times known function. You have to say, then, I'm fitting this in a very narrow space, c has to be equal to 1 over the integral over the whole plane g of xy dx dy. That's for the same reason as here. Just a density has to integrate to 1 over the whole plane. That's often the case when you want a density of a certain form. And you should also pay attention to limits of integration, because when it's not a rectangle, the limits of integration will vary from slice to slice. So just be careful about that. Okay, so conditional distribution is a bit more interesting. Let's... I just want to review the discrete case, because the discrete case doesn't involve any new theory. We already talked about this, fx, and I think I used this notation, given y equals y of x, right? That's a conditional, I did it, sorry, I'm reviewing, so I'm doing the p case, which is the discrete. So that's the probability, nothing funny, x equals x, given y equals y, okay? Probability x equals x, comma y equals y. So that's a joint divided by a marginal, probability that y equals y, and that equals p xy. So this is a review from last time, xy divided by p y of y. And also, if you wanted to do p y of y, you remember you sum over all x, just as we did, where p x y of xy. So far, so passé. Now, that was good because we already knew how to condition on an event. We divide by the probability of the event. And so it's very tempting to say, let's say x, now y is now a continuous bivariate random variable. Okay? Bivariate means two, and continuous means when we say continuous bivariate, automatically there is a joint density. F x y y. So what I want to say is what is y given x equals a particular value. And this is quite easy to see even in that region example. So, by the way, I said that the marginal distribution in this region is not uniform. It's because the slices vary in width from size to size. What about the conditional? If I condition on this value of y, is x uniform? It is. It's equally likely to be... If you remember, a uniform effectively gives each little... You can imagine you're in preschool again putting the little blocks into a large region. You're filling in a triangle or a circle with little blocks, and you have a few rough edges around the edge. But you're asking, you know, uniform chance of lying on each of those blocks. Effectively, that's what uniform per area means. And then if you're saying, well, given that I lie on a particular rung of blocks, then each block is equally likely. So the conditional density should still be the uniform density. And we're going to try to find, so conditional that you lie at an exact y value, the density has to be uniform. So we're sort of looking for that example already. But we've got a bit of an issue in doing it in full generality, because it's tempting to say, okay, so that's joint, of course. Now let's try talking about conditional f. At the moment, I'm just going to put inverted commas because it's not clear we can do this, given y equals y of x. Okay, I'm going to follow the discrete pattern. Well, there's actually going to be two problems here, one of which we can alleviate easily and one of which we can't. X equals x given y equals y. So to do the given, I'll do the comma y equals y divided by probability of y equals y. Okay, so already that's not making sense because it should have been a density rather than... Okay. So, one thing that's clear is we can't do a conditional PMF for a continuous variable. There's a reason PMFs don't make sense for continuous variables. There's 0 for joint and marginal, but for conditional it's not just 0, it's worse than that, it's 0 over 0. Remember, a continuous variable has 0 probability of lying on any point. In fact, a continuous variable has 0 probability of lying on any line whatsoever because a line has 0 area. So it's roughly area times density. So if you're on a... There's actually, if you have any 0 area region, the probability of landing in that region is 0. Whether that's a line or a circle or anything, it's just not probability 0. So we have a real problem saying let's condition on the value of y. So the first one, actually, there were two problems obtained in doing that. The x problem and the y problem. Turns out the x problem is quite tractable. For instance, we could talk about CDF. CDFs are nice because then I don't have to talk about the x equals x problem. I could talk about capital F subscript x given y equals y. Okay, so I'm still going to put inverted commas because it's still no good. Equals probability that x less than or equal to x, y equals y, divided by probability that y equals y. So I've removed perhaps one of the question marks because that at least got us away from the mass function to something that could possibly make sense. But it's still no good. It's still no good because this is 0 over 0. Okay? So that definition doesn't work. So I'm going to even give you a little quote by Kolmogorov, the father of probability theory, and we'll see how valid this quote is in a moment. The conditional probability with respect to an isolated hypothesis of probability 0 is inadmissible. Okay, so inadmissible, of course, is a fancy word saying you can't do it. Okay? So that's he's the father of probability theory, so he'd better know, and that's a good thing. So it seems like the chapter of the book has come to an untimely death, but luckily that's not the case. There is I guess, an interesting word in this quote from Kolmogorov. Any thoughts? Isolated. So that's a bit of a covering that. Isolated means just some event. So what you definitely can't make sense of in a general context is, condition on event E and probability of event E is 0, because it just never happens either way, whether with y or not. So that's the isolated aspect. So what about when it's not isolated? Well, of course, the event that y equals y, that's not exactly very isolated, because we have a continuous surface that describes the probability of this. So when we're saying condition on y equals y, I don't really care, actually, that it's not possible to land on y equals y. What I mean is, well, y can easily land very near to the exact value you're interested in, and if it does lie more give or take at that point, what does the distribution look like? Now that is an answer that can very well be answered, a question that can be very well be answered. And I'm not going to emphasize the kind of limit aspect of this, but you could imagine very well saying, let's take, instead of the slice y equals y, let's take a limit in the context where, instead of allowing y equals y, allow a epsilon error either side, so between y minus epsilon and y plus epsilon. Now, if you did that, your slice, I'm even going to try my hand at drawing a little. Okay, my slice has gone this way. You'll have to forgive the arguable swapping of now, I guess, x1 equals y, but whatever. So if I have a slice of very thin width, epsilon, I could then find the probability of lying within this slice, and the conditional probability on that slice, and I could hope the conditional probability on that slice would converge to some limit as epsilon tends to 0. And the fact is, it does converge to a limit so long as there's a little bit of continuity assumed with capital F. And the even better news is the limiting definition of it is not needed to define the conditional PMF. So I'm going to get you to try and think not so much about limits, although it can be understood as limit at a slice. Instead, we're just going to have a purely formalistic approach. So the formalistic approach is fully suggested by here. Joint PMF divided by marginal PMF. That was in the discrete case. So we're going to do the conditional density of x given y. Now, you'll note that I'm going to try to avoid the isolated hypothesis. So I'm writing it slightly different way. Instead of saying the conditional density of y given y equals a little particular value, that's kind of making it isolated. I'm considering it holistically. I know that's an overused word, but I really am considering it holistically. So given y, now it is not the particular event that matters. It is the random variable that matters. So, and we'll get to this in a context of a paradox later. It is the random variable that matters here, not the particular outcome. So the random variable matters is the function of two variables, really. F subscript x. I'll put the x given y in the subscript, but I'll also put the x given y. Now, I could write it of a function of two variables, x comma y, but it doesn't quite look so good. But so I'm going to put a vertical bar, but the meaning of that is the same as a comma. It's a function of two variables, but it just looks a bit better that way. So you'll notice this is not the same thing as I was doing here. It's not just putting the y equals y in the subscript. I really want it to be a function of two variables. Given by f, the joint divided by marginal. So as always, continuous equals joint divided by marginal, fy of y. Now, I'm just going to look, you might be wondering about uniqueness, because those who care about these things would notice that there's a little bit of non-uniqueness in the density. Whether I had a jump at whether you took the left side or the right side of a jump didn't matter. In fact, even if I put a little jump in artificially at a point, that also didn't matter. So there's a little bit of unique continuous function of x and y, so long as fxy itself is continuous. Okay, so now I know, so that's in square brackets because that's beyond what you need to worry about in general, but if you're worrying about whether this actually makes sense as a unique thing, it's not fully unique, but the continuous choice of it is unique if fxy is continuous. And just for those following on, I know we're talking about continuous random variables, but for the density to be continuous is above and beyond. That's more like the variable being smooth. That's the density being a continuous function. That rules out uniform, for instance. Uniform has a cliff, so no cliffs, no jumps, no nothing. Okay, so that's in square brackets because it's not so important. What is important is the following properties, that the integral of fx given y, x given y, dy over all y's, the integral of the conditional density is the marginal density, fx of x. So this is a very specific density for a specific point. But if you integrate it out over all possible slices you could have taken, then I just get the marginal, which is very non-specific. That's when you forget the relevant value of y. In the example 1, the integral, the actual fx given y of x given y, yeah, maybe you can do the calculation before yourself, is equal to it's actually wrong. It's very important to put in the marginal on y. Sorry about that, because this is, you should you should think about, it's like putting, just to reiterate the same equation twice, fx given y, x given y, multiplied. So conditional times marginal, so long as you do conditional x given y times marginal y, equals joint fxy, xy. So I've written the same thing twice, but and if also you might be wondering about this. This is where